And now, ladies and gentlemen, to introduce our first keynote speaker as a representative of one of our gold sponsors. CCT is the technology arm of Consolidated Contractors Company, or CCC, and they are a global self-performing contractor based in Greece with operations extending throughout the Middle East, CIS countries, and Africa. CCC is a leader in implementing BIM and project control functions, both for buildings and plants projects. In 2012, CCC received the CITES Star Award by Fiatech for its vision, innovation, and contributions to advance interoperability in engineering and construction operations. CCT has arranged for demos of their BIM system C3D during their breaks at their booth, which is in the back of the room, so I hope you take advantage of that. Would you please welcome Amer El-Sersi, the Group Manager for Learning and Innovation for Consolidated Contractors Company, who's going to introduce our first keynote speaker. And here he is. Good morning, sir. Good morning. Glad you made it.
Thank you very much. Sorry, we don't see any, roll-up banners because our stuff actually stuck in Montreal. So probably, we have the computers. We don't have the marketing material, but we promise the afternoon we'll have the marketing material also. It's my pleasure and honor to welcome Dr. Xiangyu Wang for the event as a keynote speaker. Dr. Wang is a chair professor in the School of Built Environment at Curtin University. Professor Wang is also a co-director of the Australian Joint Research Centre for Building Information Modelling. Professor Wang is an internationally recognized leader and researcher in the field of BIM, mobile computing, and virtual reality, as well as augmented reality. Dr. Wang, his contributions and applications of BIM and augmented and mobile computing in the area of architecture, engineering, and construction is supported by more than 250 papers, peer-reviewed, on this field. Please join me to welcome Dr. Wang.
I start to feel a little bit drowsy this morning, not just because that I come from all the way from the other hemisphere, but also the conference atmosphere like this make me feel like I'm in a dinner event rather than a morning breakfast event. Thank you very much, Mahat, for the introduction, and it's my great pleasure to be here to give a keynote speech about augmented reality. It's more about how to integrate augmented reality with BIM. And I would like to thank the board of directors of the aceBIM and also the sponsoring companies for this exciting event to bring me all the way from Australia to here to give a talk here. I would say that Western Australia is very similar to Alberta because they have plenty of resources and energies, and oil and gas is one of the major driving for economy. And I've been heavily working with the Woodside Energy Limited, which is the largest energy company in Australia. And I would like to start my talk with a YouTube video that we made together with the Woodside. This video, the contents of this video actually wins the runner-up award of the 2012 Curtin Commercial Awards. So if you can please bring up the...
It's difficult to conceive the scale and complexity of construction projects in the oil and gas sector. The challenges involved in managing such mega projects are enormous. Initiated by Woodside, Project EXPO uses leading-edge technology to improve productivity and performance in LNG construction. Internationally recognized leader in augmented reality, Professor Xiangyu Wang and his team Lei Ho, Matthew Lavender and Ying Wang have focused on the challenge of getting the right information to the right people at the right time to enable significant productivity gains. Using augmented reality as an enabling platform, they have developed a suite of powerful integrated software tools aimed at improving efficiencies at every stage of a project's life cycle. Their tabletop modelling tool, overlays a 3D model of a structure onto standard 2D shop drawing plans. Moving the camera allows you to move in, out and around the model. You can also scale the model up to life size and even isolate layers of the structure. Simply by scanning a marker on a component, the In Situ Asset Management tool displays a 3D model of the component and where it fits in the construction path. Depending on your role, you can also access additional information, including specifications, where it was made, when it was delivered, and when it was to be installed. The tool can also locate components by identifying where you are and where the object is in relation to you. The assembly tool locates you in a physical space and then overlays a 3D model of what needs to be assembled in that space. It shows what the component looks like and where it goes. And it provides a step-by-step animation of the exact assembly sequence. This tool directly links the virtual world to the real world.
Our innovation takes context-aware computing to the next level. Although developed with Woodside for the oil and gas sector, our innovation can be readily applied to mega projects in other sectors such as mining, health and transport infrastructure. Okay, so as you can see, we are actually doing a lot of significant research with Woodside and other industry organizations. But for confidentiality reasons, I cannot go beyond what is shown in this video. But there's a series of papers which is going to be published soon, from where you can actually learn more about that. And I would like to spend a couple of minutes to introduce the Australasian Joint Research Centre for BIM. It's actually a research centre owned by university. It's established relatively recently between China University and Curtin back in this March. And I actually bring some brochures for the BIM Center. If you need some, you can just feel free to grab. And this is university research center, so it's different from industry organization sponsored, just like aceBIM is totally different visions. We are more working on the research part of it. So this is the aim of the BIM Center. We're looking at to improve the performance and productivity of construction in other sectors by integrating BIM with other technologies such as wearable computing, augmented reality, virtual reality through research. And these are the devices that we play with. These are the toys that in our lab. And our goal is to present and provide the most relevant information to the workers or stakeholders with the least effort in how to minimize the information overload. As you can see from the video, that visualization is really, really important. The engineering part of that is important, but how you present the information to the workers is also very important, to the right time, in the right time, right place, and to the right person, and to the right job as well. A little bit about the BIM. If you look around the world, and you can realize that Australia is really late adopter of BIM as compared to the other places, especially in US and Asia areas. And that's one of our goals as well, to promote and to make aware of the adoption of BIM and best practice and benchmarking as well to the Western Australia industry. But BIM starts moving quickly in Australia. There's a Built Environment Industry Innovation Council, and they work very hard to develop the BIM standards. And there's a couple of BIM initiatives in Australia, and there's a couple of projects in Australia as well that started using BIM, but most of them are in architecture and engineering stage rather than significantly to the rest of the life cycle of the project. Autodesk classified the BIM use into 4 categories: representation, simulation, collaboration, and realization. And I would say close to 90% of BIM adoption in industry is focused on the representation and simulation. And very few actually start to look at the collaboration and realization part. And my talk today is geared more towards on how augmented reality can be used to realize BIM on the site. What is augmented reality? How many of you have heard about augmented reality before? Okay, over half. Augmented reality is basically in a digital environment where you can insert the digital information into a real-world view of the users. For example, you can wear a goggle, or you can use an iPad or iPhone, and through the special device you can see the information overlaid on top of the physical environment or physical work pieces that you're dealing with. And if you look at this spectrum, this is called the reality virtuality as continuum. Starting from the real environment is where we stay and live and work, and to another extreme, virtual environments like video gaming. They aligns a rich range of area which is termed as mixed reality here. And somewhere around here, which is closer to the real environment extreme, is augmented realities. From this example, you can see the digital information of the car design remotely is inserted into the real environment. So this is another example from colleagues in academic. This is the setup of how a GPS-based tablet can, through the tablet, you can see something like extension pipeline or something which is superimposed to an existing infrastructure. So augmented reality has been applied in many areas. Most of them are in gaming, tourism, and entertaining part of it. And just imagine that you design the pipeworks in BIM, but how do you actually communicate it to the on-site workers? There's a couple of ways. One of the ways to give them a laptop or desktop, and they can pull out the BIM 3D model and then check the BIM model with the installation space in the real world, and then to match one to the other. But what if we use augmented reality? Then you ended up with something like this. You got overview of the factory, and then you can impose the virtual. This is the virtual piping and other things on it. And from here, you can see the first-person perspective. You can see the piping, and it will be the same size, same orientation, and same materials, textures as the one that you need to build. And basically to realize what you see is what you need to build. And you don't have to go back to the 2D menus or 2D drawings or 3D models anymore. And this will be a paperless setup. And this is another example. I don't think this has been realized yet, but it's all called augmented window. From the window, it's more like iPad based. But this is not iPad, it's still under development. Through this, you can see some information. For example, somebody's on the 8th floor, if he's or not, he's in the office at the moment or not. So I would like to bring this up again, that visualization is the key, because if you look at the, but user-friendly is very important. If you look at why the iPad, iPhone is so popular, why? Because it's haptic touch, right? It's if you flip around the pictures, the photos, and it's very easy as compared to selecting a bunch of pictures in a browser-based environment. And the same thing here, we're trying to see how the BIM can be categorized in different levels and take them to the right persons through augmented reality and all other visualization. Augmented reality is just a way to presenting things, but also on the back, in the back stage, you also need the tracking and sensing technologies, you know, for example, like RFID and barcode and GPS, that sort of things. And these are the projects that have been done for the past 10 years. And I'm probably, my PhD advisor, Professor Philip Dunstan, myself, are probably the first one who created an AR application in architecture, engineering, construction arenas. I'm going to go through some of the project and present some of the research results that we found. If you look at this chart, you can easily recognize that the future technologies will focus on the features of 3D, location-based, virtual reality, augmented reality. So these are the keywords that make a new technology become more popular and have high commercial values. Location awareness basically means how the location can be interpreted automatically and then to indicate to the system and to respond accordingly. For example, presenting the right information to the right person. And this slide's already presented before. Our goal is to look at how to get to spend the least effort and present the most valuable information. It's all about interaction, integration, and interface. Interaction means how you communicate with computer, machine, and information. Integration means how you integrate the real environment with the virtual, how you integrate the information with the workpiece that you're dealing with, for example, a pipe or concrete slab. Interface is more about how user-friendly your system would be. If no matter how fancy the technology would be, if it's not user-friendly enough, nobody's going to use it. And this is one of the example we have done with the Korean university that using augmented reality plus the semantics information on, and then you can recognize the construction components, and then it will feed into the database, and then it will search the relative information that you will need, and then feed back to you through the augmented reality environment. And this is the user-centered framework of layer interaction, because it's very important not just focus on technology, but also focus on the people and the user needs. So if you look at outer ring, it is the technological components of augmented reality, and inner ring is the task requirements. Okay, your construction task require you to move a lot in the physical environment. What is your working environment? Is noisy or not very noisy? Is in high elevation or not? What is your task mental requirements? It requires you a lot of processing in the mental or not. How your hand is occupied, right? Your both hands occupied. You don't have the third hand to actually hold any display for augmented reality. So in linking between the two rings will be the user layer in the middle, and there are a lot of things that need to be considered as well. And this is the typical methodology that we use, starting from the interaction part, to look at the user needs, requirements, the task needs, and then to see what kind of technologies can be integrated. They can reach a wide range of things, and then prototype the interface and to look at how satisfactory it is for the task in the field testing, and then also refine the system as well. This is one of the very early prototype that I've been done with my PhD advisor over 10 years ago, pretty much. And this is about using augmented reality for, it's called AR-CAD system. It's basically you model things in the AutoCAD, and then you click a button, and then it will send to augmented reality, so you can review the pipe in the augmented reality environment. What basically tell you is you can, through the goggle glass, then you can rotate the tracking marker, and then there's a virtual pipe like that. Looks like a glued on it, and then you rotate 90 degrees, and pipe rotate as well. So you can look at the, you can examine the different angles of the pipe to see, to design review purpose. And this is the AutoCAD environment, send it to augmented reality. So for a very complicated piping system, you can easily recognize, you can examine the problem in it. And I'm going to skip these technical details. We have done an experiment, compare ARCAD with AutoCAD, and the conclusion is it's a very worthwhile viewer assistant tool to help to identify interferences as compared to the AutoCAD. And then we think about maybe we should bring ARCAD to the next level to support the face-to-face system for collaboration. And this is back in 2005, and look at how the AR can improve and change the way that people collaborate in design review. And this is the setup, and two people wearing the goggles, and they can see the same complicated design, and then they can collaboratively communicate with each other using this tracking ball, and then find the design errors. And then we have done an experiment to compare the paper-based 3D drawing, which is the state of the art at that moment, with the AR, and then we found out the benefits. The paper drawing consumed much more time than what the AR would do. And the finding of the differences is significant. And we also look at the NASA task workload rating index to look at how user-friendly the AR system is, and it turns out to be very user-friendly. Some questionnaire has been done, and concluding that AR system can overall better facilitate the design, collaboration, and problem solving. So for this particular experiment, 64% of time has been saved as compared to the face-to-face paper drawing tracking. And then next step from there was to how to take AR to the distributed collaboration level to look at how people in different two geographical locations can collaborate. And this is the AR setup, and this is the, we chose the Nevis work as the benchmark to compare. And then we found augmented reality can take much less time as compared to the Nevis work in design review, remotely collaboration. And again, this is NASA task load index. There's significant differences in the workload between the virtual space scenario and Nevis work aroma, and we found it's much more user-friendly in this case. And this is another example back in 2009, and using augmented reality for the distributed design. As you can see here, it's about the interior furniture design here. This is the virtual piano, and this is a real human, and this is the virtual remote collaborator avatar, and I think this is a real desk and the real room. So basically, two different rooms have mirrored the same setup, and then person in room 1 can be virtually represented in room 2, and to communicate with the real person in room 2, and vice versa as well. And they can look at the same. They can look at the same room, and then to plan out the interior design. You know, so TV hanging on the wall, and you know, piano and that sort of things. And this gentleman, this is the virtual avatar representing this gentleman in room B, and this avatar representing this lady in room A. So it's all about how to use augmented reality to support the collaboration, communication, that purpose. And this is another example that we have done using augmented reality for urban design, urban planning, and education as well. This, for the interest of time, I'm not going to go through the entire architecture, skip it, and then this is what we see on top of a map. You can put many virtual objects on. Some of them represent buildings, some of them represent street or lawn. And we have done an experiment to compare it with the wood block systems. And we found out, and we asked people to realize some design objectives using these two treatments. For example, let them to use the tool to provide a point of interest for pedestrian and tourists, or provide adaptability through development that allows future changes, the redevelopment. We'll give them some tasks for them to go through to see how many objectives they can finish using either treatment within a specific time frame. And then we found out there's not much difference between the two, actually. If you can look at the group 1, group 2, the number of objectives they realized is pretty much close to each other. So some of the conclusions, but AR still very promising because it's easy to use system, and it can reduce the possibilities of misinterpretation among the design team members. And our suggestion is to mix it with the woodblock use, and then use as a distant collaboration tool as well. This is one of the projects we have done using augmented reality for the maintenance. For the at the end of the day, each equipment operator, they can open up the engine and then check their levels of fuel and other things. So you don't need to go back to the manual system. You can only open it up, and through your glasses, and you will see those virtual tags floating around the real component, and you can recognize, oh, okay, this is a dust cap, and you need to remove the car cap, and then check and clean the inside, and then there will be a step-by-step instructions on the top right corner, and show you what's the next step we'll be doing. This is a recent study to look at how augmented reality can support the assembly with the Lego system. And this, in this is the typical assembly scenario. The human operator, they read the joints or menu and go to the each work pieces, pick them up, and put them together in the assembly area. This is probably out of battery now. But through augmented reality, what we can do is on the right picture, we actually integrate them all together to streamline the number of transitions you need to do to split your attention between different perceptual environments. And from here, you can see if I need to find a piece like this, I can just pick one and then compare it. So this is in augmented reality, this is in real. This means it's correct. This is wrong because the shape of the component is different. And also for these two examples, this is wrong because it's shorter than what you are supposed to select. And then animation can be played, one step, the other step, how the Lego system can be put them together. And this is experimental setup. And then we compare with the 3D manual on the left, and also on the right-hand side is augmented reality. We compared them together, and we found augmented reality is reducing a lot of time as compared to manual. If you look at here, it's around 7 minutes, and this is 12 minutes, so it's almost half of it. And the number of errors made during the assembly is significantly lower, 1.3 as compared to the 3.4. And we look at the learning curve as well to see how augmented reality can scaffold people to pick up assembly quickly. And the learning curve is much steeper in using augmented reality as compared to the manual. And this is another recent experiment we have done. We cannot afford the real pipe for assembly, so we go to the Bunnings. The Bunnings is probably relevant to equivalent to Home Depot in here. Is that Home Depot in here? Maybe we get the cheap pipes and put them together. And this box is supposed to represent a big exchanger in a liquefied natural gas plant. And we got all the joints from the Woodside, the industry partner. And the assembly sequence knowledge also borrowed from the industry experts. So I want to play this video to show you the sequence. So the setup here is very simple here. You see, oops, sorry. Go back here again. Can you play again, please? Yeah. So basically, these two people, they are looking at a large screen or projection screen on site, and something that you cannot see here, but they actually can see augmented reality in front of them. So, and this one is the virtual one, which we'll start with. And there's a bunch of pipes around here, and we don't know which one we should choose and which one should choose first. And then, but the augmented reality will let you know. So it will pop up with the first component, which is a T-pipe. T-pipe, and then you just follow the animation. Because there's three main mistakes in assembly. The first one is you cannot always choose the right pipe or component. The second one is your assembly path is wrong or not clear. And the last one is your assembly sequence is wrong. You put the wrong thing before you can put the before you put the right things on. So you have to remove it first and then put it on. So rework cost is a lot. And at this step, you can see this is the next step and put it on. And these red rulers are used to do the measurements. So this is the next one coming up, and you just need to look around and pick one that you suspect that fits, and then take it up, put them together, and compare it. So when you compare it, you can compare the size, compare the materials, orientation, and other things. And once you make a decision, this is the right one, and then you put it on. So, and by the way, all these animation sequence has been designed in BIM. Okay, so in BIM, when you do the 3D pipeline design, you actually design the sequence, how one should fit to another, what's the assembly sequence would be. And then those information are actually fed into augmented reality for the on-site use. So I'm going to skip that. So we have done experiment, and then we conclude that using the system that you see consumed like around 16 minutes to complete a task as compared to 34 minutes of using the traditional isometric technical drawings. So almost 50% of time is saved in this particular scenario. And then we look at the number of errors that are made by each group. And then it's also 50% of errors saved as well. So 50% errors means 50% rework is saved, which is represent dollar amount as well. And in this particular experiment, we choose a fairly simple, medium simple task to focus on. But think about in a very large scale, especially in oil and gas plant, if you scale this system up, it is very promising to save more time and reduce more errors by prediction. And then we look at these, if we compare the time use distribution of the two groups using these two systems, and you can realize that in augmented reality, the interaction with the information and search information time is significantly reduced to 49% as compared to this one with the traditional way. Okay, so the more time is saved in looking for information, then more time can be spent on the real work in assembly. Because there's a statistic in Construction Institute, Industry Institute, and they said like over 60 or 50% of time by workers on the site are used to looking for the right information. So it's less than 50% is actually consumed on the real work. So this can potentially save time as well. So that's why if you look at here, for the reassembly time is 12% as compared to the 6% assembly time for the traditional way. So the time which is available for the real job here is actually increased by using the advanced visualization techniques. So some challenges and issues for AR, just like BIM, AR is still in early stage for adoption. And three main challenges. The first one is lack of domain knowledge. Okay, what do I mean by domain knowledge? Domain knowledge means that the assembly piping scenario that you just saw in the video, right? We need the knowledge of how things can fit to each other. And the lack of evaluation as well. There's a strong need for rigorous empirical validation and evaluation. And technological limitations, for example, like the accuracy of the trackers on the site and the robust of the tracking markers as well. So this is the methodology we developed for the AR system lifecycle. So starting with the task requirements and all the way to the psychological part, define all the requirements of the system, and they evaluate and feedback to the original task to be augmented. Lack of evaluation, well, it's empty slide there, so you can see not many people are keen to evaluate how effective the system is and go ahead to claim that they're useful. Only like around 10% of augmented reality work actually mentioning about the evaluation, and all the others are about concepts and development. Technologies that can support AR include GPS, wireless communication, location-based computing, and other things. So pretty much towards the end of the presentation, I want to go through a couple of slides that representing some of the recent work, or some of the milestone work by my colleagues around the world in the same areas. One of these is by Azuma, 2001. So basically, if you want to build a pipe like this, you can just visualize it on top of the existing infrastructure. And this one is for architecture. So if you want to build a bridge over the river, what you can do is stand on the bank, and then through a special device you can see the real scale of the bridge. Look at how environmentally friendly, how aesthetical it looks like as compared to the surrounding existing environment. And I showed this example before already. And this recent development from National Taiwan University is called BIM AR helmet. They put a cell phone on the side of the helmet and linked with the projector in the front as well. So what you see is actually something like this. Okay, you can see the reinforced steels behind the walls, which is projected from the projector in front of the helmet. And you can, before you do that, you can actually choose which room you're in, and then the system can bring up the drawings for you automatically. And this is the indoor visualization, how the facilities can be visualized behind the wall, so that you can, if you want to check a particular wiring behind the wall, you can make sure that you're digging the right place, and then find out that. And this one is underground sewage piping visualization through augmented reality and GPS based. You can see the GPS antenna. And then if I found this problem in the sewage pipe coming out from this building, I can easily recognize which one of them, and then to make the digging accordingly. And this is the project from Professor Winiarski Panamara in Columbia University, using augmented reality to look at the to track the progress of behind the schedule, ahead of schedule components. The red one means behind of schedule, and the green one means the ahead of schedule or on time. So some quick summary. The hardcore engineering is very crucial, very important, the engineering design, that sort of things. But it's the way that people, workers, to use or interact with those engineering information is also very important. A poor, user-friendly integrated system is a waste of resources. A good one can save a lot of money and time as well, and added a lot of values on it. And technology is all there. It's just need a smart way how to integrate them all together by consulting with the industry people, test it, and scale it up to be implemented and used in the industry. And AR must go to the site, and BIM has to go to the site as well, and there needs to be social and contextual in the future so that it can reach its full potentials. So that's my talk, and this is my contact. If you want to know more details, please just drop me an email. I'd be very happy to respond. Thank you very much.